Today, we're diving into one of the weirdest and deadliest disasters in American history. Seriously. It's a story about a bizarre tragedy that completely swamped Boston. But the real story, the science behind it, well, it reveals a fundamental law of physics that governs life on a scale you can't even begin to imagine.
Okay, so picture this. It's Boston's North End. The date is January 15th, 1919. And for a winter day, it's kind of warm. People are out just going about their Wednesday, and they have no idea that a nearby 5-story high tank is about to unleash absolute chaos.
I mean, can you imagine being Patrolman Frank McManus? You're just making a report, and suddenly you hear this sound like machine gun fire and a horrible grinding noise. You look up, and there's a massive dark wall of liquid erupting from this giant metal tank. Your first instinct is this panicked, almost unbelievable call for help. A wave of molasses? It sounds like a joke.
But it wasn't. The scale was just immense. We're talking more than 7.5 million liters of raw, crude molasses
That just erupted through the streets, moving at a terrifying 55 kilometers per hour. That's as fast as a running horse. Before anyone could even process what was happening, the disaster had already claimed 21 lives and left another 150 people with serious injuries. The city was changed in a matter of minutes.
And the power of this thing was just unimaginable. This wasn't some sticky mess. It was an explosion. The tank literally burst apart, shooting steel shrapnel like a bomb, crushing freight cars, ripping a firehouse clean off its foundation. It even buckled the tracks of an elevated train line.
So this brings us to the big question, right? We get floods, we get tsunamis. But how on earth could a wave of something you put in cookies cause this much destruction? Why was it, in some ways, even more devastating than a wave of water? The answer, it turns out, is all in the physics of the syrup itself.
To really get what happened, we have to understand the substance at the heart of it all. Because molasses, as it turns out, is not your average liquid, not by a long shot.
Molasses is what scientists call a non-Newtonian fluid. And what that basically means is its thickness, its viscosity, isn't a constant. It actually changes depending on how much force you put on it. And believe it or not, this one property is the key to the entire disaster.
You know, you actually deal with non-Newtonian fluids all the time. Think about getting ketchup out of a glass bottle. It's totally stuck, right? But then you smack the bottom, you apply force, and whoosh, it suddenly flows out. Toothpaste is the same deal. It just sits there on your brush, but it flows easily when you squeeze the tube. That's exactly how the molasses behaved.
And this is what made the molasses wave a terrifying dual threat, and what made it so different from a tsunami. Look, both had that devastating initial impact, a high-speed wall of pure force. But here's the difference. A tsunami's water eventually recedes. The molasses, it did the exact opposite. After that violent surge, it thickened right back up into a thick, gooey, inescapable trap.
And that second phase, the trap, is where another layer of physics made this thing just so incredibly deadly. Because once you were caught in it, getting out was pretty much impossible.
To get why, we have to look at something called the Reynolds number. Now, don't worry. In simple terms, it's just a number that helps predict how an object will move through a fluid. All you really need to remember is this. For swimming, the higher the Reynolds number, the better.
And now just look at this staggering difference. For a person swimming in water, the Reynolds number is around 1 million. That's why it's easy to propel yourself forward. But in molasses, that number just plummets to about 130. And at that point, the physics of how we move completely fall apart.
At such a low Reynolds number, a normal swimming stroke is useless. See, when you push your arm back to try and move forward, the molasses is so thick and sticky that as you bring your arm forward again for the next stroke, you just pull all that same fluid right back with you. You're effectively swimming in place, just trapped.
The people and horses caught in that flood experienced this firsthand. They struggled and they just sank deeper. For us, it's this bizarre, terrifying nightmare scenario.
But here's where this story takes this absolutely incredible turn. What if I told you that this nightmare world, this experience of being trapped in syrup, is the permanent, everyday reality for some of the most common life forms on our planet? To see what I mean, we need to shift our whole perspective, from a citywide flood all the way down to the microscopic world of a single bacterium. It's a concept made famous by a physicist named Edward Mills Purcell, and he called it life at low Reynolds number. And what it means is that because microbes are so incredibly tiny,
A fluid that seems totally thin to us, like plain water, actually feels as thick and as viscous to them as molasses feels to us.
I mean, just look at the sheer scale of this difference. A human in water is at 1 million, a horse trapped in the molasses was down to 130. But a bacterium in that very same water, its Reynolds number is a tiny 0.00001. To them, water is a world far, far stickier than anything the victims in Boston ever faced.
And yet, they move. Of course they do. Life found a way. Microbes have evolved these incredible adaptations for their low Reynolds world. They can't swim like we do. Instead, they use these powerful, corkscrewing tails called flagella, or row with thousands of tiny little hairs. Some can even cleverly manipulate the fluid right around them to make it temporarily thinner, just so they can push through.
And that right there brings us to the final amazing connection. We've gone from a historic flood in a major American city all the way to the invisible world of a single microbe.
And that's the incredible takeaway here. The exact same laws of fluid dynamics, the same principles of viscosity and Reynolds numbers that made a wave of molasses so uniquely deadly back in 1919 are the very same laws that shape the struggle for survival for microbes every single day. A bizarre human tragedy and an invisible, microscopic reality, both governed by one universal law of physics.